Well, today it'll be a Klein 4 group because 2 of you will work and 2 of you will work, and those will be linearly independent until the end of class when we come together on it. But so here's what you can do with this app now. If I want to change any of the coefficients in the linear equation, I can adjust these sliders. So if I change the a coefficient, if I change it to, I don't know, -3, and let's change this d coefficient. So you'll see right away why I like this app, because everything updates kind of in real time, and we can hopefully, there we go.
The points on the line, like, the number of them change.
The number of them changes a little bit, yeah.
According to
Well, they're spaced out. They're all spaced out by 1s in the x direction. Is how they're all the same number of points. Just we can't see them all if we get off the chart too much. So now here's a different system of linear equations, and there's a little bit more going on in the algebraic solution to this, but geometrically at least, we can identify where their solution is. It's right here. And in particular, let's see if we can guess at the coordinates of this point. And again, whenever you're solving by graphing, really that's what you're doing, is kind of guessing, looking at a point. But where does it look like the location of this point is in Cartesian coordinates? Yeah, it looks like x equals -1 and y equals -1, right? So let's let that be our hypothesis. We'll be good scientists about this. Our hypothesis is that the solution of this system is x equals -1 and y equals -1. And again, what's the system? I'm just going to copy it down. Notice it's up in the title of our graph up at the top there. Y minus 3x equals 2. And 6x minus 8y is equal to 2. Notice something kind of weird that happened here is that the order of the x's and the y's is different in those two equations. This shouldn't trouble you as a mathematician, but as an aesthetic person, we might, and we frequently will this semester, want to write them so that the x's and y's are in the same order in both equations. So let's start by doing that just to make this look a little bit friendlier. So rather than y minus 3x, I'm going to write it as minus 3x plus y. In the first equation. We lose nothing because addition is commutative in writing it that way. Okay, let's solve this by elimination. So that's the one where we end up having to make a choice or two. And these are the kinds of choices we're going to start paying particular attention to tomorrow. We're going to talk about row reduction. But if I wanted to solve this by elimination, what are my options? That would actually be a substitution technique, right? If I solve for y on the top and then plug that in, yeah, that'll work, right? Y equals 2 plus 3x. And then I would substitute 2 plus 3x into the second equation and go from there. Okay, that's fine. But that's not elimination. That's substitution. So if I wanted to do this from an elimination standpoint, in other words, add or subtract the equations together to eliminate one of the variables, what are my options here? Or what do I have to do in order to make that possible? Right, why? Why would I multiply the first equation by 2? Right, so you're looking ahead here. In order to eliminate a variable, we need to make the coefficients of that variable either equal or possibly equal and opposite. Right? Equal and opposite would be nice because then we can add to cancel. And Jocelyn's noticing that the first equation multiplied by 2 makes that a reality for the x's. Because then both of the coefficients of x would be -6. So -6x plus 2y equals 4 is what we would have for the first equation. And then the second equation remains the same. Okay, so multiplying that first equation by 2 balances out the coefficients of x. Now adding these two equations together eliminates the x. So x's are gone. And then I have 2y minus 8y, -6y. And on the right-hand side, 4 plus 2, 6. So sure enough, solving this for y by dividing by -6 on both sides, we find y is equal to 1. -1, thank you. I wrote it right, and then I said it wrong. And then, again, now that we know y, we can find x by Substitute, just plugging it back into either of the first two equations. Let's say I plug it into the second equation just for the sake of argument. So 6x minus 8y, and now y is equal to negative 1, is equal to 2. And from here, it's just a couple steps to find the solution for x. Subtract 8 from both sides and divide by 6. And so, as we predicted from the graph, we got lucky. The solution of our linear system of equations is indeed x equals negative 1, y equals negative 1. So it works out. But I wanted to surface this example because there was this step we had to do. Before we could add the equations together and come up with a useful elimination, we had to modify one of the equations first by multiplying it by a number to make the coefficients equal and opposite. Because you're not going to cancel anything by adding or subtracting unless the coefficients are either equal or equal and opposite. So whichever variable you're targeting, multiply that equation by something to make it match the other. Or, if need be, multiply both equations by something to make the coefficients match up. And that's part of the art of using elimination, and as we'll see tomorrow, using row reduction, which is this same process, just boiled down to its bare essentials, ignoring all the x's and y's and equal signs, and just focusing on the coefficients, just on the numbers, is really what row reduction is. It's a systematic way of making those choices to help eliminate variables in our equations.